Now, hello again, students, and now welcome to the third theory session on biomass storage. What we are talking about are the risks and the problems associated with storing of comminuted woody material in piles. And following the previous sessions, you now have an idea of the processes and of the sequence of these processes and the organisms. But now, before you go on to the homework, I want to introduce you a little bit to the dynamics of the process and how that applies in a real pile. And then in the homework, you will apply that understanding when planning the storage facility. The difference between different biomasses are mainly which microorganisms are the most active, and the sequence in which they occur, and which conditions they prefer. Following this nugget, you will not be able to predict the probability of self-ignition in a storage. And you will not be able to stop the deterioration of the material. And you will not be able to eliminate the health hazards. But you will know a little bit about how to reduce the risks. And you will be better prepared to do a risk assessment prior to or as part of a planning process. A fairly old report from the Fire Protection Agency in Sweden concluded that there are about 200 fire incidents reported annually in connection with chip storages. And the report also contained some typical data, and the generic chips pile in this slide is based on that report. As you see in the slide, will the total volume become 3,375 meter cubed. For simplicity, we now assume the dry density of the chips as 500 kilos per cubic meter, and we assume the moisture content to be 50%. So the solid density becomes 750 kilos per cubic meter, and setting then a porosity at 45%, we arrive at a total content of 1,856 cubic meters of solid wet material, or 1,392 tons. Unfortunately, there are not so many international studies about the decomposition rates of wood chips. At least not as I have found. There are lots of old such studies in Sweden, but they would all be in Swedish. But in the references to this homework, you will find a reference to a YouTube video. That video is about composting and is a guide for gardening, but let me help you to interpret what it says. All in all is the video almost 9 minutes. Some 2 to 3 minutes into the video is shown how wood chips have completely decomposed within 1 year. To obtain such a fast deterioration, one has to add nitrogen so as to have a proper ratio of nitrogen to carbon in the substrate. To understand the significance of this, you may want to refer back to the Busy-Plan Handbook, section 432, and to the tables in that section. And for the fast composting, has the material in the video also had an addition of fungi spores to set it off. But when storing chips for energy purposes, one wants to avoid decomposition of the material. So then you do not add extra nitrogen, and you do not add fungal spores to it. About 6 minutes and 15 seconds into the video, it shows wood chips that have been lying for 1 year. To these chips has not been added nitrogen, and there has not been added any spores. About a minute later, you will see that these chips are in the process of decomposition, but they can still be easily identified as chips. About 8 minutes into the video, it is emphasized that the presence of leaves and such substrates increases the rate of decomposition. The reason for that is that these components add nitrogen, and you can see the material. In real wood chips for energy pile, there will be bark, there will be needles and such material, so it will decompose. In extreme situations, may wood chips more or less completely deteriorate in a year's time. But if it is a clean material, as shown at 6 to 7 minutes into the video, will the chips be visibly affected within a year, but not completely decomposed. The measure we tend to use in Sweden and in other countries where bioenergy is widely used is the mass loss rate as percent of the dry substance lost per month. 1% per month is a low rate. 5% per month is a high rate. 10% per month is extremely high, but might be reached in some bad cases. So let me just indicate what 1% per month actually means. As you see from the slide, the total breakdown ratio is about 2.5 to 3 grams per second. And the dry substance has a heating value about 18 to 19 megajoules per kilo. And then the rate corresponds to about 45 to 55 kilowatts. In reality, will the decomposition zone be in the center of the pile? So just assume a half circle, radius 1 meter, and extending along 90% of the pile length. The volume of that zone becomes 63 cubic meters, and then the volumetric heat load becomes almost 1 kilowatt per cubic meter. The text in the diagram is in Swedish, but what is shown is this. The vertical axis is the heat developed in watts per kilo. The horizontal scale is the sample number. The groups are, to the left, bark and conifer wood chips, kept at 30 degrees for a week and at a moisture content about 40%. Middle group, bark and conifer wood chips, kept at 50 degrees for a week, moisture content about 40%. Right, bark and hardwood chips kept at 50 degrees for a week, moisture content about 40%. There was visible mold on the hardwood chips in this group. The experiments were part of a bachelor's work done in 2010. The experiments were done so that the chips were kept in closed jars big enough to maintain a surplus of oxygen for a week at a specific temperature. A small sample of the jar contents was then transferred to a microcalorimeter and the heat development registered. The only thing I want to show with this is that heat loads about 1 to 2 watts per kilo is what you would expect, and that for a pile this size, this will correspond to a mass loss about 7 tons per month. Let's now have a look at the dynamics in the most simplified way. First, we can state that there are 4 main results of the decomposition. First, the microorganisms grow. Then heat is released. And as the third consequence, water vapor plus carbon dioxide are formed. And then the fourth consequence is that in the central zone does the temperature rise, and so does the concentration of water vapor. Sooner or later will the atmosphere in the central zone become saturated with respect to water vapor. And then will the water vapor condense in the border zone between the central warm zone and the outer layers of cold chips. The transport of water vapor and the heat release will now create new and nice conditions for new microorganisms. And this process continues until what was originally a pile of more or less homogeneous quality has become more or less a binary pile where the central parts may be as dry as less than 30% moisture, and the top and the outer part may be as wet as 70% moisture content. But the material will, on average, not dry very much, if it dries at all, and the ash content will become higher. These processes cannot be stopped, but they can, to some extent, be slowed down. The way to do that is to allow cold air from the surrounding to penetrate into the pile at the bottom. The natural draft induced by the heat developed from the microorganisms will provide the driving force for this penetration, and this airflow will then escape again along the steepest pressure gradient and carry with it the surplus heat. So a low and porous, that is a permeable, pile will maintain a cool and low active central part. Now refer back to the Busy-Plan Handbook, text section 317, and have a look at the tables in that section. Try to interpret the information from the tables in terms of nitrogen and nutrient availability and in terms of permeability in the pile. You will now have an overall understanding of how to plan your storage to reduce the risks and the material losses. So now you will want to go on to the homework session.